For centuries, black holes existed only in theory, cosmic mysteries so powerful they trap even light itself, leaving us with nothing but equations and imagination to grasp their existence. But in April 2019, humanity did the impossible. We stared directly into the heart of darkness and captured it. That first haunting image of a black hole, a fiery ring bending the fabric of space-time, wasn't just a photograph. It was a beacon of human curiosity, a moment that redefined what we thought was achievable. Think about that. Something invisible, something that defies the laws of physics as we know them, was suddenly right there on our screens. How did we get here? What did it take to turn science fiction into science fact? This wasn't just a victory for astronomers. It was a triumph for all of us, proof that when we push the limits of technology, collaboration, and sheer determination, the universe rewards us with answers. Behind that single image lies a story spanning decades, involving hundreds of scientists, telescopes the size of the planet, and algorithms that had to be invented from scratch. It's a tale of failed attempts, near impossible odds, and moments where the whole project nearly collapsed under its own ambition. And yet, against all logic, they succeeded. So what does it really take to photograph the unphotographable, to see the unseeable? This is the story of how humanity turned a mathematical idea into a tangible glimpse of the cosmos' most enigmatic phenomenon. From the minds who dared to dream it to the technology that made it possible, we're diving deep into the science, the struggle, and the sheer brilliance behind that iconic image. Because this isn't just about a black hole, it's about how far we're willing to go to understand the universe and ourselves a little better. The concept of a black hole was once pure mathematical speculation, an idea so bizarre even Einstein doubted it could exist in reality. His theory of general relativity predicted these gravitational monsters back in 1915. But for decades, they remained as elusive as ghosts. Scientists could only infer their presence by watching stars dance around invisible partners or detecting bursts of X-rays from doomed matter spiraling into the void. The idea of actually seeing one, most researchers dismissed it as fantasy. Light can't escape a black hole, so how could we ever capture its likeness? It would be like trying to photograph a shadow cast by nothing at all. Yet in the 1970s, a handful of visionary astronomers began asking a radical question: what if we didn't need to see the black hole itself? What if we could photograph its silhouette against the glowing disk of superheated gas swirling around it? The math suggested it might be possible, but the challenges were staggering. A black hole's shadow would be vanishingly small in the sky, like spotting a donut on the surface of the moon from Earth. No single telescope existed with that kind of resolution. The laws of physics seemed to conspire against the very idea, but science has always thrived on impossible questions. By the 2000s, a small team of researchers, led by Shep Doeleman at the Harvard-Smithsonian Center for Astrophysics, became obsessed with cracking this cosmic puzzle. They proposed an audacious plan. Instead of building one impossibly large telescope, they would link observatories across the globe into a virtual instrument the size of the planet. It was a gamble. The technology was untested, the funding scarce, and the odds of failure overwhelming. But the potential reward, humanity's first glimpse of a black hole's event horizon, was worth the risk. This wasn't just about proving Einstein right or wrong. It was about pushing the boundaries of what we thought we could know. What followed was a 20-year odyssey of innovation, setbacks, and sheer perseverance. The team had to invent new ways to synchronize telescopes across continents, develop algorithms to stitch together petabytes of data, and even account for the rotation of Earth distorting their observations. At every step, the universe seemed to throw up new barriers: cloudy skies, technical malfunctions, even volcanic ash disrupting signals. There were moments when the entire project teetered on collapse, when the data seemed too messy or the math too unforgiving. But the team pressed on, driven by a shared conviction that the impossible might just be waiting for someone stubborn enough to try. Einstein's equations were more than just numbers on a page. They were a roadmap to the universe's most extreme phenomena. When he published his general theory of relativity in 1915, it didn't just redefine gravity, it unveiled a cosmos far stranger than anyone had imagined. Space and time weren't static backdrops but a dynamic fabric, warped and twisted by mass. And at the heart of this revelation lay a terrifying prediction: regions where gravity became so overwhelming, the fabric of space-time itself could collapse into an inescapable pit. These were black holes, though the term wouldn't even exist for another 50 years. Even Einstein himself grappled with the idea, questioning whether nature would truly allow such monstrosities to form. Yet the math was undeniable. If enough mass squeezed into a small enough space, the gravitational pull would become infinite, creating an event horizon, a point of no return where light itself surrendered to the abyss. For decades, these cosmic traps remained purely theoretical, dismissed by many as mathematical curiosities. But the universe has a way of humbling skepticism. By the mid-20th century, astronomers began spotting bizarre celestial behaviors: stars whipping around invisible companions at impossible speeds, quasars blasting energy across billions of light-years with no obvious fuel source. The only explanation: black holes lurking in the darkness, their presence betrayed by the chaos they left in their wake. One of the most compelling clues came from the heart of our own galaxy. In the 1990s, astronomers tracking stars near the Milky Way center noticed something extraordinary. These stars weren't just drifting, they were racing in tight, frantic orbits around nothing. Their paths revealed an invisible object 4 million times more massive than our Sun, crammed into a space smaller than our solar system. The math pointed to one inevitable conclusion: a supermassive black hole, just as Relativity had foreseen. It was a eureka, a moment, but also a paradox. Scientists could map its gravitational grip, calculate its size, even measure the way it bent light, yet the black hole itself remained forever hidden. This was the puzzle that drove the next generation of astronomers to dream bigger. If indirect evidence could reveal so much, what would it take to peel back the veil entirely? The answer lay in Einstein's own work. General relativity didn't just predict black holes, it offered a blueprint for their shadows. The theory suggested that light from the superheated gas swirling around a black hole would bend into a fiery ring, outlining the void at its center. Capturing that ring wouldn't just confirm Einstein's vision, it would give humanity its first direct window into the heart of spacetime's most profound mystery. The stage was set, the equations had spoken. All that remained was to build a machine capable of seeing the unseeable. Building a telescope the size of Earth sounds like something out of a science fiction novel, but for the team behind the Event Horizon Telescope, it was the only way to solve an impossible problem. Black holes are so compact that even the supermassive one at the center of our galaxy, Sagittarius A, appears tiny in our sky, like trying to spot a grapefruit on the surface of the moon. No single telescope on Earth could ever hope to see something that small. The solution: turn the entire planet into one enormous scientific instrument. The Event Horizon Telescope wasn't a physical structure but a revolutionary network of radio observatories scattered across the globe. From the icy peaks of the South Pole to the high deserts of Chile, from the volcanic slopes of Hawaii to the mountains of Spain. By synchronizing these distant telescopes with atomic clocks precise to within a billionth of a second, scientists could combine their observations into a single, Earth-sized dish. The concept, known as very long baseline interferometry, had been used before, but never at this scale, never with this ambition. It was the astronomical equivalent of trying to conduct a symphony where every musician was on a different continent, playing in perfect time. The challenges were staggering. Each telescope had to point at the same exact patch of sky simultaneously, under clear conditions, while collecting a flood of raw data, so much that shipping hard drives by plane was often faster than transferring it digitally. One misfire in weather, one technical hiccup, and an entire night of observation could be lost. And even when everything worked, the data was so complex that it took years of algorithmic innovation just to piece together a coherent image. This wasn't just about pointing telescopes at the sky. It was about rewriting the rules of observational astronomy. What made the EHT truly extraordinary, though, wasn't just the technology. It was the human collaboration behind it. Over 200 researchers from 60 institutions across 20 countries, speaking dozens of languages, all working toward a single goal. Political borders and cultural differences didn't matter when the target was 55 million light-years away. The project demanded not just scientific brilliance but relentless teamwork, sleepless nights troubleshooting equipment, heated debates over data interpretation, and moments of shared awe when the first hints of that fiery ring began to emerge from the noise. In the end, the EHT didn't just capture an image. It proved something fundamental about how science works at its best, not as a solitary pursuit, but as a collective leap into the unknown. When the first photo of M87's black hole was unveiled in April 2019, it wasn't just a victory for astrophysics. It was a testament to what humanity can achieve when we stop thinking in terms of limits and start thinking in terms of possibilities. Not every black hole is a good candidate for humanity's first cosmic photo shoot. The Event Horizon Telescope team needed targets that balanced two crucial factors: sheer size and relative proximity. Enter Sagittarius A, the supermassive black hole at the heart of our Milky Way, and M87's colossal counterpart 55 million light-years away in the Virgo galaxy cluster. These weren't just random choices. They represented the universe serving up the best possible subjects for this unprecedented experiment. Sagittarius A had one irresistible advantage: it was practically in our cosmic backyard, just 27,000 light-years from Earth. That proximity meant its event horizon, while still vanishingly small in our sky, appeared slightly larger than more distant black holes, but our galaxy's central monster came with complications. Thick clouds of interstellar dust swirl between Earth and Sagittarius A, forcing astronomers to observe in specific radio wavelengths that could pierce the cosmic haze. Worse yet, this black hole is surprisingly restless. Its accretion disk flares and flickers unpredictably, like trying to photograph a candle flame in a windstorm. M87's black hole presented the opposite challenge. At 2,000 times farther away, its immense size became the saving grace. This behemoth weighs in at 6.5 billion solar masses, making its event horizon appear nearly as large in our sky as Sagittarius A's despite the staggering distance. Distance brought clarity too. While our galactic center's black hole dances with nearby stars, M87 sits relatively undisturbed, its glowing gas disk more stable and symmetrical, a cleaner target for reconstruction algorithms. But that 55 million light-year gulf meant collecting usable data required near miraculous precision, pushing the EHT's technology to its absolute limits. The selection process wasn't just about physics, it was about hedging humanity's bets. By observing two fundamentally different black holes, scientists could test whether Einstein's predictions held true across different scales and environments. If both shadows matched relativity's forecasts despite their differences, it would powerfully confirm the theory's universal validity. There was poetic symmetry too, one target in our galactic home, another in the distant cosmos, together spanning the vast range of our observational reach. What made these choices remarkable wasn't just their scientific merit, but their audacity. Earlier generations might have dismissed photographing either as pure fantasy. Yet by combining cutting-edge technology with ingenious problem-solving, the EHD team turned these cosmic titans from theoretical curiosities into tangible proof of nature's most extreme phenomena. The universe had provided the perfect subjects. All we had to do was learn how to see them. Sinking telescopes across continents wasn't just a challenge, it was a high-stakes race against physics itself. Imagine trying to line up a dozen cameras scattered around the world, each snapping a photo at the exact same nanosecond, while Earth spins beneath them at over 1,000 miles per hour. That's the precision the Event Horizon Telescope demanded. A single misaligned timestamp, one clock drifting a fraction of a second off, and the entire observation would unravel like a frayed rope. The secret weapon, atomic clocks so precise they'd lose less than a second over millions of years. Strapped to each telescope, these marvels of engineering used the vibrations of cesium atoms to timestamp every shred of data with flawless accuracy. But even that wasn't enough. The team had to account for the curvature of Earth, tectonic plates shifting beneath the telescopes, even the way radio waves slowed as they passed through the atmosphere. It was like tuning a grand piano while the concert hall itself was in motion. Weather became another unpredictable foe. A single storm over a telescope in Chile or a cloudy night in Hawaii could wipe out months of planning. The team waited years for the perfect alignment, all 8 observatories under clear skies simultaneously, their atomic clocks humming in perfect sync. When that rare window finally opened in April 2017, the pressure was crushing. Every second of observation cost thousands of dollars, and failure wasn't an option. Then came the data, a deluge so massive it couldn't be sent digitally. 5 petabytes worth, equivalent to a lifetime of selfies, had to be flown from observatories to supercomputers on hard drives. The South Pole's data alone couldn't be retrieved for months until winter ended. But the real magic happened in the supercomputers, where custom-built algorithms painstakingly stitched together fragments of signals into a coherent picture. It wasn't just about combining data, it was about teaching machines to recognize a black hole's shadow in what looked like cosmic static. What's astonishing isn't just that they pulled it off, but how they turned a network of Earth-bound telescopes into something greater than the sum of its parts. By harnessing the planet's rotation, they effectively created a virtual lens as big as Earth itself, a fleeting aperture that opened for mere days each year. This wasn't just engineering, it was a dance with the cosmos choreographed down to the nanosecond. The numbers alone are staggering: 5 petabytes of raw data, enough to store every single photo ever uploaded to Instagram in 2015. That's the mountain of information the Event Horizon Telescope captured during its brief observing windows, a deluge so massive it defied conventional transfer methods. Forget uploading to the cloud. This data had to travel the old-fashioned way, packed onto half a ton of hard drives and flown from remote observatories to supercomputers in Massachusetts and Germany. The South Pole Telescope's contribution alone sat frozen in Antarctica for months, waiting for the first safe flight out after winter. Processing this cosmic haystack to find the needle of a black hole's shadow required more than just computing power. It demanded entirely new ways of thinking. Traditional telescopes produced tidy images, but the EHT's data came as fragmented signals, like trying to reconstruct a symphony from scattered notes played by musicians on different continents. Each observatory captured only partial information, their combined data filled with gaps and noise. The team had to invent algorithms that could not only stitch together these fragments, but distinguish real signals from the universe's background chatter. One breakthrough came from an unlikely source: medical imaging. The same techniques doctors used to reconstruct CT scans from X-ray slices were adapted to piece together radio waves into a celestial portrait. But even this wasn't enough. The researchers developed 4 independent teams, each working with different algorithms to cross-verify their results. When all 4 methods finally converged on that now iconic fiery ring, the moment was less like developing a photograph and more like witnessing a ghost materialize from static. The real challenge lay in the uncertainty. Unlike photographing a planet or star where you know what to expect, no human had ever seen a black hole's shadow up close. The algorithms had to work without a reference image, piecing together something entirely new. At times, the data seemed to suggest multiple possible shapes. Was the ring lopsided? Were there unexpected gaps? The team spent years running simulations, testing millions of variations to ensure what they saw wasn't an artifact of their methods, but the universe itself revealing its secrets. What emerged wasn't just an image, but a validation of human ingenuity. That petabytes of raw noise could be transformed into a clean, testable prediction of Einstein's century-old equations is one of science's greatest magic tricks. It proved that even when faced with information tsunamis, patience and creativity can turn chaos into clarity. One hard drive, one algorithm, one painstaking correction at a time. Among the hundreds of scientists who made the black hole image possible, one name captured the world's imagination: Dr. Katie Bouman. At just 29 years old, this computer scientist led the development of an algorithm that turned fragmented radio waves into humanity's first glimpse of a cosmic abyss. Her contribution wasn't just technical, it was symbolic. In a field often dominated by established figures, Bouman's breakthrough proved that fresh perspectives could crack problems decades in the making. The challenge she faced would have stumped most experts. The Event Horizon Telescope's data wasn't like a jigsaw puzzle with neat, interlocking pieces. It was more like recovering a symphony from a handful of random notes played out of order. Traditional imaging techniques fell apart when dealing with such sparse, noisy signals. That's where Bouman's algorithm, CHIRP continuous high-resolution image reconstruction using patch priors, changed everything. Instead of forcing the data into existing models, her approach taught computers to recognize patterns the way humans do, filling gaps with intelligent guesses based on the physics of black holes themselves. What made CHIRP revolutionary wasn't just its technical brilliance, but its humility. The algorithm knew its own limitations, flagging uncertainties instead of pretending to have all the answers. This transparency let scientists distinguish real features from digital artifacts, critical when photographing something nobody had ever seen. Bouman compared the process to restoring a fresco where most of the plaster was missing. You couldn't just invent details, you had to let the underlying structure guide the reconstruction. The night the first image emerged from the chaos of data, Bouman's reaction said it all. A photo of her hands covering her mouth in stunned joy went viral, becoming shorthand for scientific triumph. But behind that moment lay 3 years of grueling work, false starts, and moments where success seemed impossible. Early versions of CHIRP produced smudgy blobs that looked nothing like a black hole. The team had to teach the algorithm to ignore Earth's atmospheric interference, filter out telescope quirks, and resist inventing patterns that didn't exist. Bouman's story resonates because it shatters stereotypes. She wasn't an astrophysicist steeped in relativity equations, but a computer scientist who saw the problem differently. Her breakthrough came from applying techniques from medical imaging and even social media photo filters to cosmic data. In doing so, she embodied the collaborative spirit of modern science, where boundaries between disciplines blur and innovation thrives at intersections. That iconic ring of light isn't just a victory for astronomy. It's proof that sometimes the tool you need isn't a bigger telescope, but a new way of seeing. Turning petabytes of cosmic noise into a clear image required more than computing power. It demanded a new kind of patience. The data arriving from those synchronized telescopes wasn't a neat collection of snapshots. It was more like finding pieces of 1,000 different jigsaw puzzles mixed together, with most of the pieces missing. The team faced a paradox. The very thing that made the Event Horizon telescope powerful, its Earth-sized scale, also made the data impossibly complex. Each observatory captured fragments of radio waves, but gaps stretched between them wider than oceans. Filling those voids without inventing false details became the ultimate test. Early attempts produced ghostly smudges that could have been anything, a blur that might hint at a ring, or might just be random interference. The breakthrough came from combining 4 independent imaging methods, each approaching the problem differently. One technique borrowed from radio astronomy's history, another adapted medical imaging algorithms, while others built mathematical models from scratch. When all 4 converged on the same fiery ring structure despite their different approaches, confidence grew. This wasn't digital artifice, it was the universe agreeing with itself. The process mirrored how human vision works in dim light. At first, you see nothing. Then vague shapes emerge as your brain stitches together faint signals. Finally, patterns solidify into recognizable forms. The black hole image developed similarly. Early versions showed asymmetrical blobs, but as algorithms improved, symmetry emerged. That symmetry wasn't imposed, it was uncovered, revealing the profound simplicity hidden in Einstein's equations. A perfect circle warped by gravity, just as relativity predicted. What made this painstaking work extraordinary wasn't just the technical achievement, but how it transformed our relationship with the cosmos. For the first time, humanity wasn't just calculating a black hole's existence, we were witnessing its shadow in visceral detail. That fuzzy orange ring, soon to become iconic, represented countless hours of debugging code, recalibrating instruments, and doubting results until the evidence became undeniable. Science often moves in leaps, but this leap was built on a mountain of incremental steps, each one proving that even the universe's darkest secrets can't hide forever from human curiosity. April 10, 2019 marked a turning point in human history, not with fanfare or fireworks, but with the quiet unveiling of an image so profound it silenced auditoriums worldwide. That grainy orange ring glowing against the blackness of space wasn't just a scientific achievement, it was a cosmic mirror, reflecting back humanity's relentless curiosity. The supermassive black hole at the heart of galaxy M87, 55 million light-years away, had finally shown its face, or more accurately, its shadow, a dark heart encircled by light bent so violently it formed a perfect halo. The global press conferences felt like shared revelations. In Washington, Tokyo, Brussels, and Santiago, researchers who'd spent decades chasing this moment stood before the world with something previously unimaginable proof. Not equations, not simulations, but light captured from the edge of oblivion itself. The data matched Einstein's predictions with uncanny precision, the ring's diameter aligning with general relativity's calculations to within 10%. Even skeptics had to confront the reality glowing on screens across the planet. This was no artist's rendering. It was nature caught in the act. What made the image extraordinary wasn't just its scientific value, but its visceral impact. For the first time, people could point to an actual photograph when discussing black holes, no longer abstract concepts, but tangible cosmic landmarks. Social media erupted with memes comparing the ring to everything from Tolkien's fictional One Ring to the fiery portals of superhero movies. Scientists found themselves fielding questions from schoolchildren and celebrities alike, all gripped by the same wonder. That glowing circle transcended language barriers, uniting cultures under a single, humbling truth. We live in a universe where such wonders exist, and we're clever enough to find them. Behind the euphoria lay a deeper lesson about how science unfolds. The image didn't emerge fully formed like a Polaroid snapshot. It coalesced over months of painstaking verification, as 4 independent teams working with different algorithms all converged on the same haunting silhouette. When one group's results deviated slightly, they halted publication for half a year, determined to root out any error. That rigor turned the final reveal into something rare, a scientific moment immune to legitimate doubt. Even the most cautious journals couldn't argue with light itself. Perhaps the most surprising detail was the ring's asymmetry, a brighter southern region betraying the black hole's spin, dragging spacetime around it like whirlpool currents. This wasn't just confirmation of old theories, it was new terrain for exploration. That lopsided glow hinted at the direction of rotation, the magnetic fields threading the accretion disk, even clues about how such behemoths grow. The image wasn't an endpoint, it was a doorway, swinging open onto questions no one had thought to ask before. In the days that followed, something unexpected happened beyond the labs and lecture halls. The photo became a cultural touchstone, appearing on murals, album covers, and protest signs, a universal symbol of human potential. For a brief moment, the world paused its divisions to marvel at a shared achievement that required every continent's cooperation. The telescopes in Chile couldn't have done it without those in Hawaii. The data from Spain needed the South Pole's contributions. In an age of fragmentation, that fiery ring reminded us what's possible when we align our efforts toward a common horizon. Not bad for a dark spot in the cosmos 55 million light-years away. That fiery orange ring we've all seen isn't the black hole at all. It's the absence of one, a cosmic silhouette burned into the fabric of space-time. What the Event Horizon Telescope captured was something far more mesmerizing than a simple hole in space. It was the shadow of M87's supermassive black hole, a dark void backlit by the swirling storm of superheated gas spiraling toward oblivion. This distinction matters because it reveals how black holes don't just trap light, they bend the very rules of perception. The glowing ring itself is light that shouldn't exist near a black hole's event horizon. Those photons aren't escaping the abyss, they're on a cosmic tightrope, skimming the edge of no return before being flung toward us by the black hole's immense gravity. Einstein predicted this exact phenomenon, that light from the accretion disk would curve around the black hole like water circling a drain, creating a luminous halo around the darkness. The eerie perfection of that ring, matching relativity's equations to within 10%, was the universe's way of nodding to a theory conceived a century earlier in a Swiss patent office. But the image also shattered misconceptions. Some expected a messy, chaotic blob, assuming black holes would distort their surroundings randomly. Instead, the shadow appeared remarkably symmetrical, a near-perfect circle that betrayed the elegant simplicity hidden in Einstein's math. The slight asymmetry in brightness, that brighter southern region, wasn't a flaw. It revealed the black hole's spin, dragging space-time around it like a whirlpool, causing light moving toward us to appear brighter as it gained energy. This wasn't just confirmation of old ideas, It was a masterclass in how extreme gravity orchestrates light itself. Perhaps the most profound revelation was what the shadow's size told us. That dark center isn't just empty space, it's a window into the event horizon's true scale. By measuring the shadow's diameter against the known mass of M87's black hole, scientists verified that these cosmic monsters obey relativity's strictures even under conditions no lab could ever recreate. The photo didn't just show us a black hole's shadow. It proved that, against all intuition, the universe plays by rules we can decode. What makes this image timeless isn't just its scientific value, but how it redefined public understanding. For decades, black holes in pop culture were depicted as voracious cosmic vacuum cleaners, sucking in everything nearby. The reality, as this shadow shows, is subtler. The accretion disk's orderly glow proves most matter orbits black holes for eons, like water circling a drain, with only a fraction crossing the point of no return. Even in destruction, there's structure, a reminder that the universe favors patterns over chaos. That iconic ring is more than a scientific trophy. It's a beacon from 55 million light-years away, signaling that humanity's grasp of the cosmos, however tentative, is growing surer. Every photon in that image traveled longer than our species has existed, just to tell us one simple truth: Einstein was right, and the universe is stranger than we dreamed. Those simulations weren't just computer-generated guesswork. They were the ultimate dress rehearsal for reality. Long before telescopes pointed at M87, astrophysicists had been staging cosmic performances inside supercomputers, playing out every possible way light might dance around a black hole's event horizon. Some models assumed Einstein was wrong, tweaking his equations to see if alternative theories of gravity could produce different shadows. Others accounted for wild variables. What if the black hole spun at near light speed? What if its accretion disk was lumpy or tilted? Each simulation was a meticulous thought experiment, translating abstract math into visual predictions that could be tested against the real universe. When the actual image emerged in April 2019, the resemblance to those simulations was uncanny. Not just in broad strokes, but in specific details: the precise thickness of the ring, the way one side glowed brighter, even subtle distortions in the light's polarization. It was as if nature had handed scientists a cosmic Rorschach test, and every ink-eye blot matched their calculations. This wasn't just confirmation, it was validation of a century's worth of theoretical work. The simulations had served as a bridge between chalkboard equations and tangible proof, demonstrating that our grasp of gravity wasn't just mathematical elegance, it could predict real phenomena in the most extreme environments imaginable. The process revealed something profound about how modern science operates. Those simulations weren't created in isolation, they evolved alongside the telescope technology. As the Event Horizon team refined their instruments, theorists refined their models in a feedback loop of discovery. Early simulations in the 2000s used crude approximations, but by 2017, they incorporated relativistic plasma physics, magnetic field dynamics, even the chaotic turbulence of superheated gas. This meant when the real data arrived, scientists weren't just asking, "Does this match Einstein?" They could interrogate the image like detectives, using discrepancies to probe deeper mysteries: why the ring's brightness varied, how the black hole's spin warped nearby space-time, even how energy escapes the accretion disk in powerful jets. What's often overlooked is how these simulations democratized the discovery. Teams across the globe, from Japan to Germany to the United States, ran independent models using different codes and assumptions. When all their varied approaches pointed to the same basic ring structure, it built confidence that the result wasn't a fluke of one group's methodology. The diversity of simulations became a strength. creating a mosaic of predictions that the real black hole would later mirror with startling fidelity. Perhaps most remarkably, the simulations prepared scientists for disappointment. Some models suggested the shadow might appear fragmented or obscured by intervening dust. Others warned that the black hole's spin could distort the ring beyond recognition. By confronting these possibilities head-on, researchers were ready to interpret whatever the universe revealed, even if it had contradicted Einstein. That intellectual honesty is science at its best, not seeking validation but truth, whatever form it takes. When the image aligned with the most optimistic predictions, it wasn't just luck. It was the result of leaving no stone unturned in the pursuit of understanding. The takeaway isn't just that simulations work, it's that they've become indispensable tools for exploring realms we can't yet reach. Before the EHT, no one knew if a black hole's shadow would resemble textbook diagrams or reveal something entirely unexpected. Those digital dress rehearsals turned speculation into testable science, proving that even in the face of the universe's most enigmatic phenomena, we're no longer passive observers. We can simulate, predict, and ultimately witness the cosmos playing by rules we're slowly but surely learning to decode. Within hours of its release, the black hole image escaped the confines of scientific journals and became something far more extraordinary, a shared cultural moment. That glowing orange ring didn't just grace astrophysics textbooks, it appeared on sneakers, tattoos, and late-night comedy sketches. A Korean pop band incorporated it into their music video, while bakers recreated it in fondant. Even the creators of the Doctor Who series tweaked their iconic time-traveling vortex to mirror the now famous silhouette. This wasn't just widespread interest, it was collective awe, proof that humanity still reserves its loudest cheers for discoveries that expand our understanding of existence. What made this public embrace so remarkable was its spontaneity. Unlike carefully orchestrated space missions or rover landings, the black hole image spread organically, reshaped by internet culture into something deeply personal. Memes juxtaposed the fiery ring with everything from Lord of the Rings to breakfast bagels, each joke subtly reinforcing the science behind it. When a Twitter user humorously called it a space donut, astronomers seized the moment, explaining how the comparison wasn't entirely wrong. The ring's shape did arise from matter squished flat by gravity. Science communicators had spent decades struggling to make black holes relatable. The public did it in a weekend without a single equation. The media frenzy revealed an often overlooked truth. People hunger for wonder, not just information. Major news outlets ran side-by-side comparisons of the real image with Hollywood depictions, marveling at how reality outstripped fiction. Children's shows featured segments explaining event horizons with hula hoops and glitter. Even fashion designers debuted collections inspired by the photo's eerie glow, blending art and astrophysics in unexpected ways. This cross-pollination of science and pop culture didn't dilute the achievement, it amplified it, proving that profound discoveries don't belong to labs alone. They're milestones for all of humanity to claim. Behind the viral moment lay a quieter revolution. Science educators reported surges in students asking about astronomy careers. Planetariums saw record attendance, with visitors craning their necks not just at stars, but at the newly installed black hole exhibit. The image became a shorthand for possibility, a visual anthem for what collaboration across borders could achieve. In classrooms from Nairobi to Oslo, teachers used it to spark discussions about gravity, light, and humanity's place in the cosmos. The photo's greatest legacy might be the millions who saw it and thought, if we can do this, what else is out there waiting to be found? Perhaps most unexpectedly, the image bridged divides. In an era of fragmented attention, it dominated conversations across political and generational lines. Conservative talk shows debated its implications alongside liberal podcasts. Grandparents shared news articles with grandchildren, their messages peppered with star emojis. For a brief, shining moment, the world agreed on something. Not just that the photo was cool, but that it represented the best of us. That glowing ring became more than a scientific trophy. It was a mirror, reflecting back our shared capacity for curiosity, perseverance, and sheer wonder at the universe we inhabit. The lasting impact isn't measured in citations or awards, but in quieter transformations. The little girl who tacked the image to her bedroom wall, now dreaming of telescopes. The amateur photographer who realized the same algorithms sharpening cosmic data could refine his own work. Even the skeptics who grudgingly admitted, okay, maybe science is worth funding after all. These ripples matter because they prove something fundamental, that when science dares to aim for the impossible and succeeds, it doesn't just advance knowledge. It reignites something primal in all of us, the thrill of discovery, the joy of knowing there's always more to explore. In the end, the black hole photo did more than validate Einstein. It reminded a planet of 7 billion strangers that we're all quite literally made of star stuff, gazing up at the same sky, united by questions that transcend borders. The internet may have turned it into memes, but those jokes carried an unspoken truth. This wasn't just an image. It was an invitation, one that echoed across languages and cultures. Come look. The universe is even stranger and more beautiful than we imagined. The black hole photo didn't close the book on cosmic mysteries, it tore it wide open. For all its groundbreaking clarity, that fiery ring left scientists with burning questions that redefined the frontier of astrophysics. Take galaxy formation. Why do nearly all large galaxies, including our Milky Way, harbor supermassive black holes at their cores? Is that a cosmic coincidence, or do these gravitational giants actually sculpt the galaxies around them? Some theories suggest black holes act like cosmic regulators, their explosive jets heating surrounding gas and preventing runaway star formation. Others propose they're the spark that ignites galactic evolution in the first place. The HT's image gave us a snapshot, but the movie How Black Holes and Galaxies Grow Together Over Billions of Years remains unwatched. Then there's the ultimate cliffhanger: what happens beyond the event horizon? The photo captures the point of no return, but the true nature of that darkness is still anyone's guess. Einstein's equations break down at the singularity, where density becomes infinite and space-time curves beyond comprehension. Some physicists speculate about wormholes to other universes. Others imagine a firewall of energy that vaporizes anything crossing the threshold. The paradox is haunting. We've now seen the door to this cosmic abyss, but the room inside remains locked. Even wilder are theories suggesting black holes might not be endpoints at all, but transformers, converting matter into some new form of quantum information we can't yet decode. These aren't just philosophical puzzles, they're urgent scientific targets. The next generation of the Event Horizon Telescope plans to add space-based observatories, creating an interplanetary array with resolution sharp enough to track plasma swirling near the event horizon in real time. Other projects aim to catch black holes in the act of merging, searching for gravitational ripples that might reveal what happens when two singularities collide. And then there's the Holy Grail, imaging Sagittarius A, our Milky Way's own black hole, whose flickering turbulence could teach us how these monsters feed and grow. The most humbling realization, for all its grandeur, the HT's first photo was like spotting a mountain peak from miles away. A triumph, yes, but one that reveals how much terrain still lies unexplored. Every answer births new questions, and that's the heartbeat of science. Those who call the image an endpoint misunderstand its true gift. It's not a period, but an ellipsis. inviting us to keep looking deeper. After all, the universe never runs out of wonders. It just waits for us to ask the next bold question. The next leap in black hole imaging isn't just about sharper pictures. It's about peeling back layers of cosmic reality we've never seen before. Right now, the Event Horizon Telescope's resolution is like having 20/20 vision from Earth's surface. But what if we could zoom in closer, spotting details as fine as individual photon rings, those nested halos of light orbiting just outside the event horizon? Capturing those would be like upgrading from a flip phone camera to an electron microscope. Each ring corresponds to light that looped around the black hole multiple times before escaping, creating a kind of gravitational fingerprint that could reveal secrets about the black hole's mass, spin, and even the nature of space-time itself. To achieve this, the HT team is orchestrating a global expansion worthy of a sci-fi epic. New telescopes are joining the network from Greenland to Africa, each one acting like an additional pixel in a planet-sized camera. The more telescopes added, the sharper the image becomes, filling gaps in the virtual lens Earth's geography currently imposes. But the real game changer lies beyond our atmosphere. Plans are underway to launch radio telescopes into space, linking them with ground stations to create an interferometer with a baseline stretching thousands of miles. Imagine the resolution boost when your telescope isn't limited by Earth's diameter but extends to the Moon's orbit or further. Suddenly, features that appeared blurry in M87's image could snap into razor-sharp focus, potentially revealing structures as small as a solar system near the event horizon. These upgrades aren't just technical exercises, they're keys to unlocking black holes' most guarded secrets. A sharper view could settle raging debates about whether information truly vanishes in black holes or if quantum effects leave subtle traces in the surrounding light. It might even catch glimpses of the mysterious plunging region, where gas makes its final, fatal dive past the point of no return. And let's not forget Sagittarius A, our Milky Way's own supermassive black hole. Its flickering, turbulent nature makes it a tougher target than the relatively placid M87, but the payoff could be revolutionary. Watching our home black hole's activity in real time might show how these cosmic beasts influence galactic evolution, like catching a dragon in the act of shaping its own terrain. What makes this next phase extraordinary isn't just the technology, but the collaboration fueling it. Over 30 countries now contribute to the HT, with institutions from Mexico to China building specialized receivers to capture higher frequency radio waves. These upgrades aren't competing, they're converging, like tributaries feeding a mighty river of discovery. Even amateur astronomers are getting involved, with citizen science projects helping to analyze the flood of new data. This isn't just science progressing, it's humanity collectively stretching its observational muscles, proving once again that when we pool our curiosity, even the universe's darkest corners can't stay hidden forever. The ultimate goal, turning black hole imaging from a spectacular one-off into a routine tool, a cosmic stethoscope, letting us listen to the heartbeat of gravity itself. Future observations might track changes over months or years, revealing how black holes breathe as they consume matter. Some theorists dream of capturing a black hole's shadow during a star's violent disruption, watching how the aftermath warps the image. Others speculate about detecting subtle shifts in the photon rings that could hint at physics beyond Einstein's theories. Every new pixel in this grand cosmic portrait won't just answer old questions, it'll pose new ones, ensuring the golden age of black hole exploration has only just begun. Black holes don't just bend, like they twist the very rules we thought governed reality. The Event Horizon Telescope's landmark image did more than confirm Einstein's predictions. it exposed cracks in our understanding of the universe's deepest laws. At the edge of that fiery ring, where gravity warps space-time into a funhouse mirror, physicists are staring into a battlefield between relativity and quantum mechanics, two theories that have never peacefully coexisted. General relativity paints black holes as smooth, predictable objects, while quantum mechanics insists information can't simply vanish. Yet every particle swallowed by a black hole seems to defy that principle, vanishing without a trace. This isn't just academic squabbling, it's a crisis at the heart of modern physics, and the EHT's observations are providing the first experimental clues to resolve it. Take the black hole's shadow itself. Its near-perfect symmetry aligns beautifully with relativity's equations, but zoom in closer, and quantum effects should start fraying the edges. Some theories suggest the event horizon might not be the smooth point of no return we imagine, but a seething quantum foam where space-time itself fractures into uncertainty. Future EHT upgrades could detect these microscopic tremors, offering the first direct evidence of quantum gravity, a theory that's eluded scientists for nearly a century. Imagine the implications. If we can spot quantum fluctuations near a black hole's edge, we might finally understand how gravity operates at the subatomic level, bridging the gap between the cosmos and the quantum realm. Then there's the mystery of black hole entropy, a concept so bizarre it rewrote thermodynamics. In the 1970s, physicist Jacob Bekenstein calculated that black holes must possess entropy, a measure of disorder proportional to their surface area. This was shocking. Entropy usually depends on volume, not boundaries, yet black holes seem to encode information on their event horizons like cosmic hard drives. Stephen Hawking later showed they also emit radiation, slowly evaporating over eons. The EHT's observations of M87's black hole provided indirect support for these ideas, as the glowing ring structure hints at the chaotic turbulence of particles near the horizon. It's as if the universe is whispering that black holes aren't just destroyers, they're archivists, preserving information in ways we're only beginning to decipher. Perhaps the most mind-bending implication lies in holography. Some theorists propose that our three-dimensional reality might be a projection from information stored on a two-dimensional surface, like a cosmic version of a hologram on a credit card. Black holes, with their information-packed event horizons, could be natural holograms encoding everything they swallow onto their surfaces. If the EHT can eventually detect subtle patterns in a black hole's shadow variations in polarization or photon ring vibrations, it might reveal whether space-time truly has a pixelated underlying structure. This wouldn't just explain black holes, it could redefine our entire conception of reality, suggesting the universe itself operates like a vast, interconnected computation. What makes this era extraordinary is how observation is finally catching up with theory. For decades, physicists debated black holes in the abstract, relying on thought experiments and chalkboard math. Now we have empirical data light from the edge of oblivion against which to test these wild ideas. The EHT isn't just a telescope, it's a time machine, offering glimpses of physics under conditions so extreme they mimic the universe's first moments. Every photon in that image is a messenger from a realm where the familiar laws of physics break down and new rules emerge. The stakes couldn't be higher. Unifying relativity and quantum mechanics isn't just about tidying up equations, it's about uncovering the operating system of the cosmos. Black holes are the ultimate laboratories, nature's way of pushing matter, energy, and space-time to their limits. By studying them, we're not just exploring distant anomalies, we're probing the very framework that makes reality possible. And if history is any guide, every time humanity peers deeper into the abyss gazes back, and teaches us something profound about ourselves. Behind every line of code and every telescope alignment stood people whose names we'll never see in headlines: engineers who spent Christmas Eve recalibrating receivers in sub-zero temperatures, graduate students who pulled all-nighters debugging algorithms while their coffee went cold, and technicians who braced against high-altitude winds to protect delicate instruments. The black hole image wasn't just stitched together from radio waves, it was woven from thousands of human stories, each one a thread in this cosmic tapestry. Take the team at the South Pole Telescope, where winter temperatures plunged to -100 degrees Fahrenheit. Just loading data onto hard drives became a race against frostbite, fingers cramping inside thick gloves as they worked in brief, frantic bursts between heater blasts. Then there were the engineers at Mexico's Large Millimeter Telescope, who once hauled replacement parts up the volcano on their backs after a supply truck got stuck in mud, determined not to miss their precious 8-hour observation window. These weren't just technical hurdles, they were tests of grit, where failure meant waiting another year for Earth's orbit to realign the telescopes. The emotional toll ran just as deep. One researcher confessed to keeping a crumpled printout of an early failed reconstruction in her wallet, a smudged blob that looked nothing like a black hole, to remind herself how far they'd come. Another spoke of lying awake at 3 a.m., haunted by the fear that after decades of work, the universe might reveal something that shattered Einstein's theories, leaving them to deliver the news that physics itself needed rewriting. The weight of that responsibility pressed heavier than any deadline, yet for every moment of doubt, there were flashes of serendipity that felt like the cosmos cheering them on. Like the time a power outage in Hawaii forced the team to improvise with backup generators, only to discover the temporary setup reduced radio interference, yielding cleaner data than ever. Or when a programmer's toddler, playing with a toy microphone, accidentally inspired a new approach to filtering background noise, a reminder that breakthroughs don't always come from labs, but from life itself. What united them wasn't just shared expertise, but shared vulnerability. When the first coherent image finally emerged from the chaos of data, hardened scientists reportedly wept, hugged, or simply sat in stunned silence. One technician described it as like hearing a symphony after years of rehearsing single notes. That moment laid bare the truth behind all great discoveries. They're never just about data points or equations, but about people stubborn enough to believe the impossible might take a little longer. The real magic of the Event Horizon Telescope lies not in its Earth-spanning scale, but in how it revealed humanity at its collective best, not as rival labs or competing nations, but as a species that can turn scattered starlight into understanding. Those late nights and frozen fingers, the coded jokes hidden in algorithms, the makeshift whiteboards crammed with half-erased equations, they're the unspoken verses of science's greatest poems. And like the black hole's shadow itself, they remind us that even in the darkest voids, light finds a way. Funding a telescope the size of Earth wasn't just a scientific challenge, it was a financial tightrope walk over an abyss of skepticism. The Event Horizon Telescope's budget didn't come from a single source but from a patchwork of international grants, university endowments, and even crowdfunding campaigns, each dollar a hard-won victory. Governments hesitated to invest in what some dismissed as black hole tourism, while academic committees questioned whether the project could survive its own ambition. At one point, the team resorted to repurposing decades-old radio dishes to save costs, proving that groundbreaking science sometimes requires duct tape ingenuity alongside cutting-edge tech. The numbers tell their own story. While Hollywood spends $200 million on a single space-themed blockbuster, the EHT's entire annual budget hovered around $10 million less than the cost of a single fighter jet. Researchers became masters of frugality, scheduling observations during off-peak telescope hours and writing grant proposals that framed black hole imaging as everything from a test of relativity to a driver of technological spin-offs. One engineer famously salvaged a critical component from a decommissioned weather satellite, joking that black hole hunters couldn't afford cosmic indigence. Yet the financial scramble revealed an uncomfortable truth about modern science. Unlike the Apollo era's blank check nationalism, today's big discoveries rely on fragile alliances between nations with competing priorities. European funding cycles didn't align with American fiscal years, while political tensions sometimes froze collaborative channels mid-project. The HT survived by becoming a masterclass in diplomatic finesse, framing black holes as universal heritage rather than national trophies. When a key Chilean observatory faced budget cuts, astronomers from 5 continents petitioned their governments to fill the gap, arguing that losing one telescope would blind the entire network. What's often overlooked is how this financial patchwork became the project's unexpected strength. With no single entity footing the bill, the EHT avoided becoming hostage to any one agenda. Private donors like the Gordon and Betty Moore Foundation provided flexibility for high-risk experiments, while National Science Foundation grants ensured long-term stability. Universities contributed not just funds but graduate students' cheap labor by budget sheets, but priceless in their fresh perspectives. This diversity of backers created a safety net. When one funding stream dried up, others could temporarily carry the load. The real economic revelation came in the aftermath. That single image of M87's black hole generated over 4 billion media impressions worldwide, a publicity windfall no tourism board could buy. Tech companies soon adopted the EHT's algorithms for everything from medical imaging to wireless networks, proving that fundamental research often pays dividends no spreadsheet can predict. Perhaps most tellingly, the project inspired a surge in STEM enrollments, particularly among women and underrepresented groups, a demographic return on investment that will shape science for decades. At its core, the EHT's funding saga challenges how we value curiosity. Those millions didn't just buy a photo, they purchased a new lens through which humanity sees its place in the cosmos. When the first image went viral, a donor who contributed $50,000 emailed the team, "I've funded startups that made me richer, but this made me prouder." In an age obsessed with quarterly profits, the black hole image reminded us that some breakthroughs resist monetization not because they're worthless, but because they're beyond price. That iconic image of the black hole didn't just spark scientific debate. It ignited a quiet revolution in who gets to claim ownership of cosmic discovery. On one side stood the researchers and institutions who'd poured decades and millions into the Event Horizon telescope, arguing their investment entitled them to first rights over the data. On the other, open science advocates insisted such a foundational piece of knowledge belonged to humanity itself, not just those who'd pointed the telescopes. This wasn't just about credit, it was a litmus test for how we handle scientific treasures in the digital age. The tensions surfaced quickly. When the EHT team released the first image in April 2019, they simultaneously published 6 companion papers in a single scientific journal, a move some critics called gated access to what should have been immediate public property. The team defended their approach, explaining that rigorous peer review required temporary exclusivity to prevent misinformation. But the underlying question lingered when science relies on global collaboration. Who gets to decide when and how its fruits are shared? The very telescopes that captured the data were funded by taxpayers across multiple countries, yet the raw observations initially remained locked behind academic paywalls. This dilemma mirrors larger battles in open science. Just as the Hubble Space Telescope's images became cultural commons, many argued black hole visuals should follow suit. But unlike Hubble, which is NASA-funded and thus bound by U.S. open access policies, the EHT's patchwork funding created gray areas. Private foundations, international consortiums, and university donors all had competing expectations about data rights. Some partners feared premature release could allow rival groups to swoop in and publish first, jeopardizing years of work. Others worried about corporations monetizing the images without contributing to the science. Imagine a black hole logo slapped on energy drinks or cryptocurrency ads. Yet the counterarguments held weight too. Making all data immediately public could overwhelm servers and spawn flawed analyses by well-meaning but underqualified enthusiasts. There's precedent when the European Space Agency released raw comet images from the Rosetta mission. Internet sleuths discovered everything from alien bases to spacecraft debris, creating headaches for scientists battling misinformation. The EHT team ultimately struck a compromise, releasing the processed image publicly while staggering access to raw data, allowing verification before full democratization. What makes this debate so pivotal is how it reflects shifting norms in knowledge ownership. Centuries ago, astronomers like Galileo guarded discoveries as personal trophies. The 20th century saw science become more collaborative but often siloed behind institutional walls. Now, the digital era demands new frameworks, ones that balance legitimate interests of funders and researchers with the public's right to marvel at what their collective tax dollars and crowdfunding helped achieve. The black hole image may have been processed in labs, but it was made possible by a web of contributions spanning continents and cultures. Perhaps the most telling development came months after the reveal, when the EHT team open-sourced key algorithms, enabling schools and amateur astronomers to process black hole data on home computers. This gesture, small but symbolic, hinted at a future where cosmic discovery isn't just something we consume, but something we co-create. The next frontier isn't just sharper images, it's redefining who gets to participate in the epochal moments of scientific revelation. After all, a black hole may not care who observes it, but humanity absolutely should care how those observations are shared. That grainy orange ring has done more than advance astrophysics, it's rewired how we teach the cosmos. Walk into any middle school science class today, and you might find students sketching the black hole's silhouette alongside the solar system, their crayons clumsily capturing what telescopes took decades to reveal. Professors report undergraduates arriving with questions about event horizons that would have stumped graduate students a generation ago. This isn't just a shift in curriculum, it's a seismic change in how young minds engage with the universe's grandest mysteries. Take the way physics is now taught. Before the photo, black holes were abstract equations on whiteboards, Schwarzschild radii and singularity theorems that felt disconnected from reality. Now, educators start with the image itself, using it as a gateway to explore gravity, light, and spacetime. One teacher in Texas transformed her classroom into a makeshift event horizon telescope, with students playing the roles of different observatories, synchronizing their observations using walkie-talkies. The lesson stuck not just because it was fun, but because it mirrored real science happening in their lifetimes. The ripple effect extends beyond astronomy. Math teachers use the black hole's shadow to demonstrate how geometry bends under extreme conditions, while philosophy professors debate whether a photograph can ever truly represent an object that destroys information. Even art students study the image composition, analyzing how color choices shape our emotional response to scientific data. This cross-disciplinary resonance turns a single snapshot into a master key, unlocking curiosity across subjects that rarely overlap. Perhaps most powerfully, the image has democratized cosmic wonder. For students in underfunded schools without planetarium access, that glowing ring is proof they don't need billion-dollar labs to participate in discovery. Citizen science projects now invite classrooms to analyze real EHD data, spotting patterns that might lead to breakthroughs. A seventh grader in Ohio famously noticed an anomaly in a public dataset that researchers had overlooked, her sharp eyes earning her a co-author credit on a peer-reviewed paper. Moments like these shatter the myth that science belongs only to elites in ivory towers. The true legacy might be invisible for decades. Somewhere today, an 8-year-old is staring at that black hole poster on their bedroom wall, not yet knowing that fascination will propel them toward a PhD. A community college student is scribbling questions in a notebook, unaware they'll one lead the next generation of telescopes. That's the magic of this image. It didn't just capture light from 55 million years ago. It's igniting sparks that'll illuminate the future of exploration, one curious mind at a time. The moment the black hole image went viral, something unexpected happened. Science collided with the media machine. While most coverage celebrated this historic achievement, a troubling pattern emerged. Some outlets couldn't resist twisting the facts into sensational headlines. Einstein proven wrong, screamed one tabloid, despite the image being a near-perfect match for his predictions. Another claimed scientists had solved black holes, as if centuries of mystery could be neatly wrapped up in a single snapshot. These weren't just harmless exaggerations, they created a distorted version of what the image actually represented, turning nuanced discovery into oversimplified clickbait. One particularly egregious example came from a tech blog that superimposed the black hole's glowing ring onto a sci-fi movie poster, suggesting it revealed interdimensional portals. Never mind that the photo showed nothing of the sort. It was a triumph of gravitational lensing, not science fiction. Even reputable news channels fell into the trap, with anchors mislabeling the glowing ring as the black hole itself rather than its shadow. These inaccuracies might seem minor, but they matter. When complex science gets flattened into sound bites, it erodes public understanding of how discovery really works: slow, messy, and always open to revision. The irony is that the truth was dramatic enough without embellishment. The real story, how hundreds of scientists across the globe collaborated for decades to capture light bending around a cosmic abyss, didn't need hype. Yet in the race for clicks, nuance often got left behind. Some outlets cherry-picked quotes from researchers about unexpected features, framing them as revolutionary anomalies rather than the normal uncertainties of cutting-edge science. Others ignored the painstaking peer review process, implying the image was snapped like a tourist photo rather than reconstructed from years of data. This media frenzy highlights a deeper challenge in science communication. When discoveries compete with celebrity gossip and viral trends for attention, accuracy can lose out to spectacle. The public deserves better than oversimplified narratives that turn black holes into mystical portals or Einstein into a straw man. Good science journalism should bridge the gap between complexity and clarity, not sacrifice one for the other. After all, the awe of this image wasn't in fake revelations. It was in the very real achievement of seeing, for the first time, the invisible laws of physics made visible. The fallout wasn't all negative, though. The exaggeration sparked important conversations about scientific literacy. Educators seized the moment to explain why headlines often distort research, while scientists took to social media to debunk myths in real time. Even the missteps had value. They showed why we need more voices who can translate cosmic wonder without losing the science. Because in the end, the black hole photo wasn't just a test of telescopes. It was a test of how well we can share the universe's secrets without breaking them. Long before telescopes could capture their shadows, black holes already haunted human imagination, not as astronomical objects, but as metaphors made flesh. Artists have painted them as cosmic whirlpools sucking in color and meaning, while poets liken them to the voids we confront in grief or transformation. The eerie orange ring of the HT's image didn't just validate Einstein, it handed creatives a new lexicon for the ineffable. Suddenly, the abstraction of event horizons became tactile, their gravitational pull echoing in everything from album covers to protest art. One striking example, a Berlin-based collective projected the black hole onto the Brandenburg Gate, its glow dissolving into pixelated static, a visual meditation on how even the most solid truths can fray at the edges. Philosophers, too, seized on the image paradoxes. That glowing ring is both presence and absence, a tangible imprint of something fundamentally invisible. Thinkers drew parallels to Plato's cave, where shadows hint at deeper realities, or to Buddhist concepts of emptiness as fertile ground for potential. The existential dread black holes once symbolized now shares space with something subtler, or at a universe that balances destruction and creation so precisely. When the HT photo dropped, a theology professor at Oxford famously quipped, "God might not play dice, but she certainly knows how to spin a singularity." Literature's relationship with black holes evolved overnight. Where sci-fi once portrayed them as narrative traps, plot devices to erase characters or enable time travel, authors now weave in real physics. A Pulitzer-winning novel reimagined the accretion disk's glow as a metaphor for memory, each photon a story circling the void of forgetting. Even children's books began depicting black holes not as monsters, but as cosmic recyclers, their gravitational might shaping galaxies like unseen hands molding clay. The image's impact rippled into unexpected corners. Fashion designers draped models in gowns mimicking the ring's asymmetry, while video game studios hired astrophysicists to render black holes with unprecedented accuracy. A ballet troupe in Seoul choreographed a piece where dancers orbited a projected shadow, their movements echoing the warped spacetime around M87. These responses reveal something profound. Science doesn't just feed culture facts, it offers new ways to feel. That grainy orange circle became a mirror, reflecting back our collective yearning to find patterns in chaos, to stare into the abyss and see something recognizable staring back. What makes this cultural moment unique is its reciprocity. Artists aren't just borrowing from science, they're enriching it. A sculptor's interpretation of a black hole's spin inspired a physicist to model new accretion disk dynamics. A filmmaker's speculative depiction of photon rings led to fresh algorithms for analyzing EHT data. The line between observer and observed blurs, just like light at the event horizon. Perhaps that's the ultimate lesson. In our quest to comprehend the cosmos, equations and oil paints, radio telescopes and sonnets are all just different languages whispering the same question. What does it mean to exist in a universe where such wonders drift like dark ships through the night? While M87's black hole dazzled the world with its iconic portrait, our own galactic neighbor Sagittarius A holds secrets just as compelling. Lurking 27,000 light-years away at the Milky Way's core, this smaller but sprightly counterpart presents a radically different challenge for astronomers. Imagine trying to photograph a hummingbird mid-flight versus an eagle gliding on steady thermals. That's the difference between capturing Sagittarius A and its more photogenic cousin. Where M87's black hole sits relatively still, its accretion disk glowing like a serene cosmic halo, Sagittarius A is the astrophysical equivalent of a strobe light. Gas clouds whip around its event horizon at dizzying speeds, flaring unpredictably as they spiral inward. These rapid changes mean its silhouette flickers and morphs over mere minutes, a far cry from M87's weeks-long stability. The effect trying to image Sagittarius is like assembling a jigsaw puzzle where the pieces keep changing shape. Yet this volatility makes Sagittarius a uniquely valuable. By comparing these two cosmic extremes, one a placid giant, the other a turbulent dynamo, scientists are piecing together how black holes behave across different sizes and environments. M87's 6.5 billion solar masses make it a gravitational titan, its immense size smoothing out chaotic motions. Sagittarius A, by contrast, weighs a mere 4 million suns, allowing astronomers to study how smaller black holes interact with their surroundings. It's the difference between observing ocean tides and whitewater rapids. Both reveal gravity's handiwork, but at vastly different scales. The observational hurdles don't end there. While M87's distance gives it a stable appearance, Sagittarius suffers from our too close perspective. Earth's position means we're peering through the Milky Way's crowded central plane, where dust clouds scatter radio waves like fog diffusing streetlights. Researchers must filter out this cosmic static while accounting for distortions caused by our own atmosphere, a problem M87's edge on view largely avoids. What makes Sagittarius worth the effort are the questions only it can answer. Its rapid flickering offers a real-time laboratory for studying how black holes consume matter. Do they gorge in steady streams or erratic gulps? The flares bursting from its vicinity might reveal how magnetic fields channel energy into those spectacular jets seen in larger cousins. And because it's our closest supermassive black hole, subtle wobbles in nearby stars could betray the presence of smaller black holes orbiting it, cosmic minnows circling a shark. This tandem study is rewriting astrophysics textbooks. Where once black holes were treated as uniform oddities, we now see them as diverse as galaxies themselves, each with its own personality shaped by mass, spin, and cosmic neighborhood. The serene majesty of M87 and the tempestuous nature of Sagittarius aren't contradictions but complementary pieces of a grander puzzle. Together, they're teaching us that understanding black holes isn't about finding a one-size-fits-all theory, but learning to speak the subtle dialects of gravity's most extreme poetry. The algorithms that pieced together the black hole's portrait weren't just tools, they marked the dawn of a new era in cosmic exploration. Machine learning has become astronomy's silent partner, tackling problems that would have paralyzed human researchers. Take the Event Horizon Telescope's data deluge 5 petabytes of radio waves so complex that traditional processing methods would have taken centuries to decode. AI sliced through that chaos like a cosmic scalpel, separating signal from noise with a precision that bordered on clairvoyance. But this was just the opening act. The same techniques that reconstructed M87's fiery ring are now training their sights on even grander mysteries, proving that artificial intelligence isn't just assisting science, it's redefining what's possible. Consider exoplanet hunting. NASA Kepler telescope collected light curves from over 200,000 stars, each flicker potentially betraying an orbiting world. Human analysts could process maybe a few thousand. AI systems like Google's neural networks discovered 2,000 new planets in Kepler's archives, including Earth-sized candidates hiding in plain sight. These algorithms detect dips in starlight so subtle they'd make a seasoned astronomer blink, spotting patterns across years of data in minutes. The implications are staggering. What took decades of manual labor now unfolds in real time, with machines flagging promising targets for human follow-up. It's not replacing scientists, it's giving them superhuman eyesight. Dark matter research is undergoing a similar revolution. For 40 years, physicists have chased this invisible substance that outweighs normal matter 5 to 1. its presence inferred only by gravitational fingerprints. Now, AI is mapping its shadowy web by analyzing distortions in billions of galaxy images, a task akin to tracking a ghost by the breeze it leaves in a crowd. At Stanford, neural networks recently identified unexpected clumps in dark matter distributions that could rewrite theories about how the universe's scaffolding formed. These aren't incremental advances, they're seismic shifts, powered by machines that learn from data without human bias, revealing connections we might have missed for centuries. The true power of AI lies in its ability to surprise us. At Cambridge, an algorithm designed to classify galaxy shapes stumbled upon a rare population of red spirals, galaxies that shouldn't exist under current models. In Chile, machine learning passed atmospheric data from Mars to pinpoint methane spikes that could hint at subsurface life, narrowing targets for future rovers. These aren't just faster versions of human analysis. They're new ways of seeing, uncovering celestial oddities that defy textbook categories. The most exciting discoveries often come from anomalies, and AI excels at finding the cosmic outliers that challenge our assumptions. Yet for all its prowess, artificial intelligence remains a collaborator, not a conqueror. The EHT's algorithms didn't interpret the black hole image. Human scientists decoded its implications, debated its quirks, and connected it to Einstein's century-old vision. AI lacks the curiosity to ask why the universe works as it does, or the imagination to theorize about realities beyond the data. Its role isn't to replace human intuition, but to amplify it, handling the computational heavy lifting so researchers can focus on the big questions. Like a telescope extending our vision, machine learning extends our cognitive reach, but the wonder, the storytelling, the relentless pursuit of meaning. That's still ours. The frontier ahead is breathtaking. Projects like the Vera Rubin Observatory will generate 10 terabytes of data nightly, more than the entire Hubble archive every 48 hours. Facing this fire hose of information, AI won't just be helpful, it'll be essential. Already, systems are being trained to predict supernova before they brighten, decode gravitational waves from colliding neutron stars, and even search for alien technosignatures in radio static. The black hole image was a proof of concept, a glimpse of a future where humans and machines explore the cosmos in tandem, each pushing the other toward horizons we can't yet imagine. What makes this partnership profound isn't just the speed or scale it enables, but the way it reshapes discovery itself. For millennia, astronomy progressed through patient observation, one person, one telescope, one painstaking measurement at a time. Now we're building tools that can scan the skies with inhuman patience, process information at inhuman speeds, and spot patterns invisible to human eyes while we focus on asking better questions. The universe hasn't changed, but our ability to listen to its whispers has. And if the black hole image taught us anything, it's that when we expand how we see, the cosmos rewards us with sights beyond our wildest dreams. The Event Horizon Telescope didn't just capture a black hole, it redefined how science operates on a planetary scale. This wasn't a project owned by one nation or institution, but a symphony of coordination across borders, time zones, and political climates. From the snowbound isolation of the South Pole Telescope to the high-altitude deserts of Mexico's Sierra Negra, each observatory brought something irreplaceable to the table. The ALMA array in Chile contributed unmatched sensitivity, while Hawaii's James Clerk Maxwell Telescope added crucial high-frequency data. Like a cosmic relay race, each facility passed the baton of observations as Earth's rotation brought new stations into alignment with their target. But what's truly revolutionary isn't the technical achievement, It's the blueprint this collaboration leaves for tackling humanity's next great challenges. Consider the logistical ballet required to keep this network humming. When telescopes in Spain and Hawaii needed simultaneous clear skies, teams monitored weather forecasts like generals planning a moon landing. Language barriers dissolved as researchers from Japan, Russia, and the United States troubleshooted equipment glitches over midnight video calls. At one point, a volcanic eruption in Chile threatened to disrupt data transport until Mexican astronomers rerouted hard drives through alternative flights. These weren't just operational hurdles, they were stress tests for international trust, proving that when the stakes are high enough, competition gives way to collective purpose. The AHT became a living counterargument to the notion that science flourishes in isolation, showing instead how diversity of thought and geography can sharpen discovery. The project's governance structure reads like a diplomatic masterclass. Decision-making wasn't dictated by funding percentages, but through consensus among over 60 institutions, each respecting the other's expertise. Taiwanese programmers worked alongside German theorists, while South African engineers fine-tuned algorithms developed in Boston. At times, cultural differences surfaced. Some teams preferred hierarchical approvals, others leaned into flat organizational structures, but the shared goal forged compromises. When tensions arose over data access timelines, the solution emerged from an unexpected quarter. A junior researcher from Lithuania proposed staggered releases that balanced open science with legitimate concerns about academic credit. This wasn't just conflict resolution, it was the birth of a new playbook for multinational research. What makes the EHT's model so vital for our fractured world is its demonstration of curiosity diplomacy. While political negotiators hammered out trade deals, these scientists were quietly building something more enduring, a network of goodwill cemented by shared wonder. The telescope in Spain's Sierra Nevada became a neutral ground where American and Iranian astronomers compared calibration techniques. Russian and Ukrainian researchers, despite escalating tensions back home, collaborated on noise filtering algorithms because the data demanded it. These interactions didn't make headlines, but they created human connections no sanction or border wall could erase. Science became the universal language, and the black hole its Rosetta Stone. The ripple effects are already visible. Inspired by the EHT's success, 30 nations have drafted similar frameworks for upcoming megaprojects like the Square Kilometre Array and the Lunar Gateway. Even beyond astronomy, climate scientists are adopting its governance models for international carbon monitoring systems. There's growing recognition that the existential challenges we face, pandemics, ecological collapse, energy transitions, require the same collaborative muscle the EHT flexed. When COVID-19 vaccine developers shared genomic data across continents, they cited the black hole image as proof that transparency accelerates progress. Perhaps the most poignant lesson lies in what went unsaid during the project's decade-long run. No one demanded passports be checked at telescope doors or patents filed on data processing techniques. The unspoken agreement was simple: some truths belong to everyone. In an age where algorithms divide us into echo chambers and supply chains become political weapons, the EHT stands as a beacon of what's possible when we channel our shared hunger for understanding. That glowing ring in the Virgo cluster isn't just a black hole's shadow. It's a mirror reflecting humanity's best self back at us, proving that even across chasms of difference, we can still align our gaze toward common horizons. The black hole image wasn't just built by scientists in lab coats, it was powered by teachers, students, and amateur astronomers who turned their home computers into virtual telescopes. While the Event Horizon Telescope's dishes scanned the skies, A parallel network hummed quietly in living rooms and dormitories across the globe. Ordinary citizens donated their idle computing cycles through platforms like Einstein at home, creating a distributed supercomputer that processed background data while they slept. A high schooler in Norway once woke up to discover her laptop had helped calibrate interference patterns from the Alma array overnight, her device momentarily becoming part of the world's most advanced radio telescope. This wasn't passive participation, it was active discovery. When the EHD team released portions of raw data to Zooniverse's citizen science platform, armchair researchers uncovered anomalies professional astronomers had missed. A retired engineer in Florida spotted irregular fluctuations in one telescope's timestamps that turned out to be critical for synchronization. A graphic designer in Kenya, analyzing publicly available light curves, identified a previously unnoticed pattern in Sagittarius A's flickering behavior. These contributions weren't just helpful, they challenged assumptions about who gets to do meaningful science. The project's lead data scientist later admitted some of their most innovative noise filtering techniques came from suggestions emailed by amateur enthusiasts. The tools lowering these barriers were often ingeniously simple. One open-source app let users compare simulated black hole shadows with real data through an intuitive swipe interface, left for theory, right for observation. What began as an educational tool unexpectedly became a quality control checkpoint when thousands of users collectively flagged subtle inconsistencies in early image reconstructions. Other platforms gamified the process, awarding digital badges for classifying interference patterns or tagging turbulent features in accretion disk models. These weren't just outreach gimmicks, they produced publishable results, with several citizen scientists earning co-authorship credits in peer-reviewed papers. Perhaps the most profound impact was on education. Middle school teachers incorporated EHD data analysis into math lessons, letting students measure the black hole's shadow diameter to calculate its mass. A viral social media challenge had amateur astronomers pointing home-made radio antennas toward M87, their combined backyard observations creating a surprising calibration baseline. Even failed attempts carried value when a crowd-funded attempt to image Sagittarius A using repurposed satellite dishes fell short. The team published their failure journal, transforming setbacks into teaching moments for the next generation. This democratization reveals a seismic shift in how science operates. Gone are the days when cutting-edge research happened behind ivy-covered walls. Today, breakthroughs emerge from global collaborations where a tenured professor's insight might be refined by a teenager's coding hack or a retiree's keen eye for patterns. The black hole image didn't just capture light bending around an event horizon. It reflected a new era where curiosity, not credentials, defines who gets to explore the cosmos. And that might be its most enduring legacy, proof that the universe's greatest mysteries don't belong to elites, but to anyone willing to look up and wonder. Behind every algorithm and telescope alignment in the Event Horizon Telescope's triumph stood a quiet revolution, women rewriting the narrative of who belongs in astrophysics. While the black hole image made headlines globally, the untold story is how female scientists like Dr. Katie Bouman and Dr. Heino Falk didn't just contribute to this breakthrough, they redefined leadership in a field where women account for less than 20% of senior positions. Their work wasn't about filling quotas, it was about proving that diverse perspectives aren't just welcome in science, they are essential to its progress. Take Bauman's now famous algorithm, CHIRP. Her background in computer science, not astronomy, became her superpower. Where traditional approaches struggled with sparse data, her outsider's perspective spotted solutions others overlooked, like adapting techniques from medical imaging to stitch together cosmic fragments. Meanwhile, Dr. Sarah Isayon, another rising star on the EHT team, spent nights analyzing polarized light from Sagittarius A, her findings challenging assumptions about magnetic fields near event horizons. These women weren't tokens, they were trailblazers whose work expanded the very boundaries of what we thought possible. The ripple effects transcend individual achievements. When the EHT's first image was unveiled, young girls worldwide saw something unprecedented: female scientists explaining complex physics on global stages, their names scrolling alongside Einstein's in press releases. Social media erupted with photos of daughters posing beside posters of Bouman, their Halloween costumes swapping princess gowns for lab coats and black hole diagrams. Teachers reported a surge in girls asking how to join astronomy clubs, while universities noted increased applications from women to astrophysics programs, a phenomenon educators dubbed the Bouman effect. Yet the path wasn't without obstacles. Many women on the EHT team faced subtle biases, from assumptions they were junior staffers to having their ideas overlooked until male colleagues repeated them. Dr. Lindy Blackburn, a key data analyst, once recounted presenting findings only to be asked if she'd assisted on the research rather than led it. These microaggressions highlighted why visibility matters, not as symbolism but as proof that brilliance isn't gendered. When the EHT deliberately featured female researchers in press materials, it wasn't tokenism, it was course correction. What's unfolding now is bigger than one project. The EHT's culture of inclusivity, from child care support during observation, runs to mentorship programs pairing senior female astronomers with students, has become a blueprint for other collaborations. Telescopes from Chile to South Africa now host outreach initiatives where schoolgirls interact with scientists who look like them, dismantling the stereotype that astrophysicists must fit a certain mold. The data backs this up. Papers with diverse authorship teams, including gender diversity, receive more citations and produce more innovative solutions, a trend the EHT exemplified. The real breakthrough isn't just that women helped photograph a black hole. It's that their presence normalized the idea of women shaping cosmic discovery. When Dr. Isayon recently led observations of Sagittarius A, no one questioned her authority. When Bouman testified before Congress about AI's scientific potential, she wasn't introduced as a female scientist, but as an expert, period. This shift reflects a deeper truth. Inclusivity isn't about lowering standards, it's about widening the talent pool so the best minds rise, regardless of gender. The legacy lives on in quieter moments, a fifth grader scribbling black hole equations next to her doodles, a PhD candidate citing Bouman's work in her thesis, a telescope control room where women now occupy half the seats. These aren't just milestones, they're seismic cracks in the glass ceiling of STEM, proving that when we remove barriers to participation, humanity's view of the universe gets clearer. After all, black holes don't discriminate based on who observes them. Why should we? For every groundbreaking success in science, there are 100 unseen failures, and the quest to photograph a black hole was no exception. The Event Horizon Telescope's journey was littered with nights where the universe seemed determined to say, "Not today." Imagine the frustration of teams stationed at telescopes from Hawaii to the South Pole, poised to capture history, only to be thwarted by a sudden storm or a malfunctioning receiver. In April 2017, during a critical observation window, half the network went dark when a rare cosmic ray burst fried sensitive electronics at two key sites. The team had spent years preparing for this exact alignment of Earth's rotation, and in moments their window slammed shut. Weather was the most fickle adversary. At the Large Millimeter Telescope in Mexico, perched atop a dormant volcano, Thick clouds could roll in without warning, scattering the precious radio waves needed to piece together the black hole's silhouette. Researchers recalled nights spent staring at real-time weather maps, watching a storm system creep toward their site like a slow-motion disaster. One technician described the agony of hearing rain hit the dome minutes after synchronization began, knowing the data they'd just collected was now useless static. Even the South Pole's crystalline skies offered no refuge. Its brutal winters meant any equipment failure between February and October couldn't be repaired until spring, leaving gaps in the global dataset. Technical gremlins struck with equal malice. Atomic clocks, the heartbeat of the entire network, occasionally drifted out of sync by microseconds enough to ruin an entire night's observations. During one fraught attempt to image Sagittarius A, a software bug caused telescopes in Spain and Chile to record at slightly different frequencies, rendering their data incompatible. The glitch wasn't discovered until weeks later when analysts noticed eerie discrepancies in the timestamps. Then there were the silent failures, times when everything seemed to work perfectly, only for later scrutiny to reveal subtle calibration errors that had crept into the data like invisible ink. But here's the twist: these failures became the project's secret curriculum. Each setback forced innovations that ultimately strengthened the results. When volcanic ash disrupted signals from Chile, engineers developed new error correction algorithms resilient to atmospheric interference tools, now used in everything from satellite communications to medical imaging. The cosmic ray incident led to hardened electronics that made future observations more robust. Even the weather woes had an upside. By studying how clouds distorted radio waves, teams created sophisticated models to subtract atmospheric noise from their data, a technique that later proved crucial for sharpening the final image. The true lesson wasn't just about troubleshooting, it was about redefining success. Early in the project, a young postdoc burst into tears after realizing her painstakingly collected data was corrupted by a faulty cable. A senior astronomer sat her down and shared his own hall of shame, a folder of failed observations stretching back 20 years. "Science isn't a straight line to truth," he told her. "It's a maze where every dead end teaches you how to find the real path." That mindset shift permeated the EHT culture. Teams began hosting failure debriefs, where they dissected mistakes without blame, mining them for insights. One engineer's notebook famously read, "Today's disaster, receiver array overheated. Lesson, even black holes need cooling." Perhaps the most profound takeaway was how these struggles humanized the process. While the public saw a polished final image, scientists made sure to highlight the years of frustration behind it, the crumpled notes, the coffee-fueled all-nighters, the moments when giving up seemed rational. By doing so, they demystified science, showing it as a gritty, iterative dance with the unknown rather than a parade of flawless triumphs. That transparency resonated far beyond academia. When a high school robotics team in Detroit faced their own setback, they emailed the EHT asking how to cope. The response came from Dr. Bouman herself. "The universe doesn't keep score of how many times you fall. Just whether you get up one more time than you quit." In the end, those lost observations weren't wasted. They became the foundation for a resilience that no textbook could teach, the kind that turns obstacles into stepping stones. Every clouded-out night, every frozen hard drive, every misaligned timestamp was a reminder: science doesn't demand perfection, it demands persistence. And when the first black hole image finally flickered onto their screens, it wasn't just a victory over cosmic distances. It was a testament to every time they chose to try again. That first snapshot of a black hole's shadow was like pressing pause on a cosmic dance, but the real show is just beginning. Scientists aren't satisfied with static images anymore. The next frontier, capturing black holes in motion, transforming that iconic fiery ring into a flickering movie that reveals how these gravitational monsters devour matter, warp space-time, and launch jets of energy across galaxies. Imagine watching a black hole's silhouette ripple as it swallows a star, or seeing its accretion disk pulse like a heartbeat over months of observations. This isn't science fiction, it's the ambitious goal of next-generation projects already underway. The key lies in upgrading the Event Horizon telescope from a cosmic camera to a full-fledged observatory. Plans for an expanded array, nicknamed the NGHT Next Generation HT, read like a wish list for interstellar detectives. New telescopes in Namibia, Greenland, and the Canary Islands will fill critical gaps in Earth's virtual lens, boosting resolution by a factor of 10. But the real game changer, adding super-sensitive receivers that capture higher frequency radio waves, like switching from standard definition to 8K. These upgrades won't just sharpen details, they'll allow astronomers to track changes over days or hours instead of years. Suddenly, phenomena that appeared frozen in the first image, like plasma knots spiraling toward the event horizon, could become dynamic scenes in an ongoing cosmic drama. Space-based additions could shatter current limitations entirely. Proposals to position radio telescopes in lunar orbit or at gravitationally stable points between Earth and the Sun would create baselines thousands of miles long instead of Earth's 8,000-mile diameter. Picture this, a telescope array where one dish orbits Mars while another hovers near Venus. Their combined vision sharp enough to spot individual photon rings, those ghostly halos of light that loop multiple times around a black hole before escaping. Each ring encodes information about the black hole's spin, mass, and even the nature of space-time itself, like tree rings recording cosmic history. The scientific payoff would be staggering. Real-time imaging could settle debates about whether black holes have hair, a whimsical term for subtle surface features predicted by some quantum gravity theories. Watching Sagittarius flare up after consuming a gas cloud might reveal how magnetic fields channel energy into those famous relativistic jets. There's even speculation about capturing the plunging region, a mysterious zone just outside the event horizon where matter makes its final, fatal descent. Current telescopes see this area as a blur, but future arrays might distinguish individual plasma clumps stretching like cosmic taffy as gravity overwhelms them. Beyond technology, this leap demands new ways of thinking. Processing video from an Earth-sized telescope isn't just about more computing power, it's about teaching AI to predict a black hole's next move. Teams are developing neural networks trained on millions of simulations, enabling them to fill gaps between observations like a film restorer repairing damaged frames. Other researchers pioneer algorithms that can isolate a black hole's voice from the cosmic static, not actual sound, but subtle variations in brightness that betray underlying physics. These tools won't just animate black holes, they'll translate their hidden rhythms into something we can comprehend. What makes this endeavor extraordinary isn't just the potential discoveries, but how it redefines our relationship with the cosmos. For millennia, humans observed celestial objects as static points of light. The ability to watch a black hole evolve in real time, to witness space-time itself flex and ripple, would mark a paradigm shift as profound as Galileo turning his telescope skyward. The first photo was our baby step into this new era. The coming films, they'll be our sprint toward understanding gravity's darkest, most dynamic masterpieces. Black holes twist time itself like taffy stretched to its limit, a reality far more bizarre than any Hollywood script. While movies love showing astronauts plunging into black holes to leap across centuries, the truth involves subtler, yet no less mind-bending physics. Einstein's theory of general relativity predicts that gravity doesn't just bend space, it slows time. Near a black hole's event horizon, where gravity becomes unimaginably strong, clocks would tick infinitely slower compared to those on Earth. To an outside observer, someone falling in would appear to freeze in place, their signals redshifted into oblivion. But here's the catch: for the person crossing the horizon, time flows normally. This paradox isn't a time machine, it's a cosmic tug of war between perspectives, revealing how relativity warps our most fundamental experiences of reality. The idea of black holes as time tunnels stems from speculative solutions to Einstein's equations, like wormholes' theoretical shortcuts through spacetime. Some mathematically permissible models suggest that certain black holes could connect to distant points in time or space, but there's a universe-sized asterisk. These hypothetical passages would require exotic matter with negative energy to stay open, a substance we've never observed. Even if they existed, the forces inside would shred atoms into spaghetti long before any hope of traversal. The closest real-world analog, the way black holes warp the light from stars behind them, creating gravitational lenses that act like natural cosmic zoom lenses, distorting, not transporting. What's often overlooked is how black holes don't just bend time, they reveal its fluidity. Imagine two astronauts, one orbits a black hole while the other stays far away. When they reunite, the orbiting astronaut might have aged minutes while decades passed for their counterpart. This isn't science fiction. It's the proven time dilation effect, observed with atomic clocks on airplanes, just amplified to extremes. Black holes are nature's ultimate time capsules, not because they enable travel, but because they showcase time as a malleable fabric, woven tightly into the universe's structure. The real breakthrough isn't fictional time travel, it's how black holes force us to rethink causality itself. Quantum physics hints that information swallowed by black holes might not vanish but could be encoded on their surfaces, a holographic echo of what fell in. If true, this could rewrite our understanding of time's arrow, suggesting that past, present, and future might be more intertwined than we thought. While we're light years from building a DeLorean, studying black holes' time warping effects could unlock secrets about the universe's birth or even its eventual fate. The irony: to peer into these mysteries, we don't need wormholes. We just need patience, precision, and the humility to accept that nature's truths are often stranger than our wildest stories. That first haunting image of a black hole's shadow wasn't an ending. It was a key turning the lock on a door we've barely begun to open. Think about how far we've come. Just over a century ago, black holes were mathematical oddities so controversial even Einstein doubted their existence. Today, we've not only proven they're real but captured light bending around one's event horizon like water circling a cosmic drain. This leap wasn't just about better telescopes or faster computers. It was a triumph of human imagination, our ability to conceive of the inconceivable and then build the tools to make it visible. What makes this moment so pivotal is how it reshapes what we believe is possible. For generations, black holes existed at the boundary between science and philosophy, objects so extreme they blurred the line between physics and metaphysics. Now, armed with that fiery ring of radio waves, we've crossed a threshold. The same techniques that brought an invisible singularity into focus are already being adapted to probe other cosmic enigmas. Dark matter's ghostly tendrils, the quantum foam of spacetime, even the birth cries of universes beyond our own. The Event Horizon Telescope didn't just give us a photo, it handed us a new lens through which to interrogate reality itself. Yet for all we've gained, the revelations have only deepened the mystery. That iconic image confirmed Einstein's predictions with stunning precision, but it also exposed gaps in our understanding, subtle asymmetries in the ring's brightness, unexpected turbulence in the accretion disk. These anomalies aren't flaws in the data, they're cosmic breadcrumbs hinting at physics beyond relativity, perhaps even clues to unifying gravity with quantum mechanics. The universe, it seems, enjoys showing us just enough to keep us hungry for more. The true legacy of this achievement lies in its proof that no challenge is too great when humanity aligns its collective genius. Consider the scale of collaboration. Radio dishes on 4 continents synchronized to atomic clock precision. Petabytes of data painstakingly pieced together by algorithms that didn't exist a decade ago. Hundreds of researchers speaking dozens of languages united by a single question. In an age of division, the black hole image stands as a beacon of what we can accomplish when borders blur in pursuit of shared wonder. Now the horizon stretches before us, alive with possibility. Next-generation telescopes will transform that static snapshot into dynamic films, capturing black holes as they flare, spin, and consume matter in real time. Space-based arrays could image the supermassive behemoth at our galaxy's heart with enough detail to spot individual stars whipping past its event horizon. Some teams are even developing techniques to photograph a black hole's shadow in X-rays or infrared, each wavelength revealing new layers of its violent ballet. But beyond the technology, beyond the papers and prizes, this moment has given us something far more precious, a renewed sense of cosmic humility. That tiny, glowing ring, suspended in the void 55 million light-years away, is a mirror reflecting our own small but stubborn brilliance. We are fleeting creatures on a pale blue dot, yet we've stretched the boundaries of perception to touch the edge of oblivion itself. And if we've learned anything from this journey, it's that the universe rewards audacious questions. So we'll keep asking, keep building, keep reaching, because the greatest discoveries aren't just those we've made, but those still waiting in the dark, ready to step into the light.